Now let's learn about some important stages involved in a metallurgical operation. Important stages in metallurgy. Important stages in metallurgy, let's learn. The important stages are A. Concentration of ore, B. Conversion of ore into metal oxide. Whatever metallic compound is there, say it is sulfide or carbonate or sulfate, whatever it is, it has to be transformed into oxide, metal oxide. Then the third stage is reduction of metal oxide. Reduction of metal oxide. It is at this stage you get metal. Metal oxide is reduced to metal. And then finally, the last stage is refining of metal. In the previous stage you get a crude metal, so it has to be refined, purification of metal. So these are the important stages involved in any metallurgical operation. The first stage is concentration of ore. This involves removal of impurities present in the ore, dressing or benefaction. Then you have the next stage, that is conversion of ore into metal oxide. Because suppose if the ore is a metal sulfide, you prefer transforming it into metal oxide because it is more easier to reduce a metal oxide rather than reducing metal sulfide. Then the next stage is reduction of metal oxide. Here you use some reducing agent and you transform the metal oxide into metal. And then finally it is refining of metal, that is purification of metal. We'll look at each step separately, one by one. This is the general practice. It is not always true, but in majority of cases, in majority of metal extractions, these are the stages involved. Of course, there are cases where we don't transform metallic compound into its oxide. In case of, for example, hydrometallurgy, or in case of electrometallurgy, we don't do it. We'll learn about it separately. This is a conventional metallurgical operation I am discussing here. Let us start with concentration of ore. As I told you, concentration of ore is also called as ore dressing, also called as benefaction. Fine. Here what we do is ore minus impurities, we get what is called as concentrated ore. This is what we are going to do under this section, concentration of ore. Ore minus impurities. We are removing impurities from the ore. These are earthy impurities. Earthy impurities. The various methods of concentration of ore. There are several methods available for concentration of ore. We'll be discussing one by one, and the method we adopt depends upon the nature of compound present in the nature of metallic compound present in the ore and the nature of impurity associated with it. Number one is leviation, also called as gravity separation. This is based on difference in the specific gravities of metal compound and impurity present in the metallic compound. We exploit the difference in the specific gravities of the metallic compound and the impurities present in the metallic compound. We use upward stream of water. We run upward stream of water, then what happens, and we use powdered ore. It is run on powdered ore. Ore has to be made into fine powder and we use upward stream of water. Then what happens? Lighter particles of gangue, impurities, they are washed away and the heavier particles of the ore stay back, remain, and in this way you get rid of most of the impurities. Lighter particles of impurities are washed away. I told you we are exploiting difference in the specific gravities of the metallic compound present in the ore and the impurities present in the ore. We take powdered ore and we run upward stream of water, and the lighter particles of impurities are washed away and heavier ore particles remain. So in this way it is possible to separate. Example is hematite is concentrated in this way. Hematite is Fe2O3 and it contains SiO2 as impurity. This is the impurity present in the hematite ore. These particles, Fe2O3 particles, are heavier and SiO2 particles are lighter. So when you run a stream of water, these are washed away along with water. The next method for the concentration of ore is electromagnetic separation. Electromagnetic separation. Here we make use of two rollers. There is a conveyor belt on the rollers. These are the two rollers and they are connected through a conveyor belt. This is a magnetic roller and it is being rotated like this, and from here you introduce powdered ore. Let me tell you, this method is adopted when one of these substances, either impurity or your ore, is magnetic and the other one is non-magnetic. So here we are exploiting difference in the magnetic nature of impurity and the compound to be purified. We have a non-magnetic roller here and a magnetic roller. These are connected through a conveyor belt, right? And powdered ore is being poured from one end. So what happens, the two substances, magnetic and non-magnetic substances, they fall down as two separate heaps. The point where the belt leaves the roller, here the magnetic substance will separate from the belt and it will fall down here. This is the non-magnetic substance. Non-magnetic substance. And this is magnetic substance. Magnetic substance will leave the belt at a point where the belt is leaving the roller. I'll give you example. Example 1 is SnO2 is an important ore of tin called as cassiterite, or stannic oxide is a chemical name. Popularly the metallurgical name is cassiterite. This consists of iron tungstate. This is magnetic. So this will fall down as impurity during electromagnetic separation. Another example is Fe3O4. This is non-magnetic. This is magnetic. Fe3O4 is magnetic. So these are the two examples of ores where this is magnetite ore, this is cassiterite. These are concentrated by electromagnetic separation. In the first case, the impurity is magnetic. In the second case, the ore is magnetic and impurities are non-magnetic. That is about electromagnetic separation. The next method we are going to discuss is froth flotation method of concentration of ore, froth flotation. This method is applicable for sulfide ores. This method exploits the difference in difference in the wettability of ore and impurities. If the ore is wetted with oil and the impurities are wetted with water, then you can use froth flotation technique for concentration of ore. You know, sulfide ores are hydrophobic and these are wetted with oil. So you need to use a mixture of water and oil and produce lot of froth, and the ore particles which are hydrophobic and which prefer to get wetted with oil will stick to the froth. You collect the froth, and when the froth collapses you can recover the sulfide ore. So this method is based on difference in the wetting characteristics of ore and impurities. This method is applicable for sulfide ores. Applicable for sulfide ores because sulfide ores are hydrophobic and they are wetted with oil. Look at this. Example is CuFeS2, chalcopyrites, also called as copper pyrites, ZnS, called as zinc blende, PbS, called as galena. These ores are concentrated by froth flotation technique. Now how this is done, I am going to show you with the help of this example. You need to take a tank filled with water. This has water and oil, two substances. One is going to wet impurity, the other one, oil, is going to wet sulfide ore. This is an agitator. If you rotate this is an agitator. The liquid gets agitated. From here you need to blow air. Inside you have water and oil. You are agitating the mixture and then you are also blowing air. So a froth is formed on the surface. This froth is formed due to oil. So this is the froth. And what settles down here is siliceous impurity. Froth plus sulfide ore. Sulfide ore will stick to the froth and it will come up on the surface. Now you can recover all the froth, allow it to collapse, and you can get the sulfide ore from it. Here you need to be familiar with some important terms. Collector. Collector is a substance which increases wettability of ore with the oil. Fatty acids, pine oil are used as collectors. Then you have stabilizers. Stabilizers increase the stability of froth. Phenols, cresols, especially aniline, cresols, they are used as stabilizers here. And then there is another term called as depressant. I'll explain you about depressant. First I'll let you know about collector once again. Collector increases wettability of sulfide ore with oil. Pine oil, fatty acids, xanthate esters are used as collectors. I'll repeat: xanthate esters, pine oil, fatty acids, long chain fatty acids are used as collectors. Phenols, especially cresols and aniline, can be used as a stabilizer. It helps in the increasing the interaction between aqueous phase and the oil, water and oil system. It stabilizes it. And then depressants. Depressants, I'll talk about role of depressant after this. Just look at the diagram once again. You have a large tank containing water and oil. You add, you agitate the mixture and then introduce air also. Froth is produced. The ore particles stick to the froth. The heavy particles of SiO2, I mean the hydrophilic particles of impurity will settle down and the froth is removed. It is allowed to collapse to recover oil as well as the ore. Let's emphasize on the role of depressant in froth flotation technique. What is the role of depressant in the froth flotation technique? Consider this ore, galena. Galena is always associated with ZnS impurity. This is galena. Galena is an ore of lead. This ZnS in galena is impurity. Now, when you do froth flotation of galena, there is every chance that both PBS and ZnS will stick to the froth. You want to suppress ZnS. So, to suppress ZnS from sticking to the froth, we need to add a substance called as depressant. Here, NaCN acts as a depressant. So, what happens, ZnS will react with NaCN and transforms itself into Na2 ZnCN taken 4 times, sodium tetracyanozincate 2. This is the substance formed due to the reaction between sodium cyanide and zinc sulfide. Now, chemical nature of the substance, zinc compound has changed. It used to be hydrophobic, now it has become a soluble substance. So, during the froth flotation of galena, add sodium cyanide, then sodium cyanide selectively combines with ZnS and will not allow ZnS to stick to the froth. So, only PBS will stick to the froth and you can recover it. So, here NaCN is said to be acting as a depressant for ZnS. If you don't use this, then both ZnS and PBS will stick to the froth and the separation of these two would have been very difficult. So, at this stage only during froth flotation, we add NaCN and see to it that ZnS is transformed into a soluble substance. So, this is said to be acting as depressant. So, when you have a mixture of two sulfides in a sulfide ore, then one of them is transformed into some soluble complex by adding a substance which is called as depressant. So, depressant is a substance which transforms one of the sulfides into a soluble substance and will not allow it to get attracted to the froth during froth flotation. NaCN acts as a depressant for ZnS during the froth flotation of galena. I would like to add one more piece of information regarding froth flotation technique. Look at this. An important ore of zinc is zinc blende. Zinc blende is chemically, it contains ZnS and here PBS is present as an impurity. This is the impurity present in zinc blende. Now, again during froth flotation, there is a possibility that both ZnS and PBS can get attracted to the froth. So, we need to avoid these two together getting attracted to the froth. So, what we do is we add little oil. First, we add very little oil and do the agitation so that all the PBS gets preferentially absorbed on the froth, and this froth is removed and then more oil is added. Again, this agitation is continued. So, this time ZnS gets attracted to the froth. So, this is how it is possible to have selective adsorption of ZnS on the froth. You can avoid mixture of PBS and ZnS getting attracted to the froth. first add little amount of oil, do the froth flotation, then you will be able to remove all the PBS. Then you need to add more oil and continue the agitation, then ZNS will get absorbed to the froth and it can be recovered. That's about froth flotation. I'll repeat, froth flotation technique uses difference in the nature of impurity, wetting nature of impurity and the ore. It is applicable for sulfide ores. Sulfide ores get attracted to the froth, impurities remain in the water. Another method of concentration of ore is leaching. Here we have ore plus impurity, that is impure ore. Our intention is to get rid of impurity. We add a suitable solvent, then we get a solution of the ore. We select a solvent in which ore alone is soluble, impurities are insoluble. Suitable solvent. A solvent, here we are exploiting difference in the chemical behavior of ore and impurity. We use a solvent in which ore is soluble and impurities are insoluble. So we get a solution, and then impurity does not dissolve in the solvent, then this is filtered out. At this stage, impurity is filtered out. Now, from solution, we recover ore by suitable treatment. From the solution, it is possible to recover ore. You have an impure ore, you add a solvent which can only dissolve your ore, it will not dissolve the impurity. Then we get a solution. That solution is filtered to remove the impurities. After the removal of impurities, the solution is suitably treated to recover the ore. Let us take specific example and try to understand what is leaching. Leaching involves use of solvent, some reagent, some solvent or reagent is used which can dissolve ore but not impurity. Let's look at an example of leaching. Number 1. Let's call it example 1. I have bauxite. Bauxite consists of Al2O3.2H2O. This is associated with the impurities are titanium dioxide, silicon dioxide, iron oxide. These are the impurities present in the bauxite ore. Let us see how these are removed by leaching. Bauxite ore is treated with sodium hydroxide solution at about 500 Kelvin, about 30 atmosphere pressure, high pressure and high temperature. Then what happens, all the Al2O3 will dissolve as NaAlO2 and SiO2 also will dissolve as Na2SiO3. These two are soluble substances. Two components, the ore and one of the impurities got dissolved in the sodium hydroxide. These are the substances, and the impurities Fe2O3 and TiO2 are filtered out. They are removed. Now, in this solution, you can as well write it like this: AlOH taken 4 times. This is same as NaAlO2. To this, we add carbon dioxide in aqueous solution. Then you get Na2CO3. You also get Al2O3 dot XH2O. This can also be represented as AlOH taken thrice, aluminum hydroxide. Then this substance dot XH2O is ignited and you get anhydrous Al2O3. This is the purified bauxite. Now during this process, SiO2 is not recovered. When you are passing, see, the solution is alkaline, this solution is alkaline. To the alkaline solution, we are adding carbon dioxide with the intention of neutralizing it. So when you do that, Al2O3 comes out first, SiO2 will not get a chance to come out because SiO2 is more acidic than Al2O3. Al2O3 is amphoteric, whereas SiO2 is acidic, predominantly acidic. So SiO2 remains in solution as sodium silicate only, but this NaAlO2 sodium metaaluminate comes out as a precipitate Al2O3.XH2O. And moreover, during this process we add a crystal of Al2O3 which acts as a seed. It is called as seeding. We add a crystal of Al2O3 which will speed up formation of more Al2O3 in the solution. This is filtered out and then it is ignited to get pure Al2O3. So this is an example of leaching. We have exploited this nature of these two substances. These two are soluble in alkali and these two are insoluble. So you got rid of these two impurities, then you could selectively precipitate out Al2O3, heated it to get anhydrous alumina. This process is called Bayer's process. It is Bayer's process of concentration of bauxite. Another example of leaching is you can see during extraction of silver and gold. Look at this. Example 2. This is an ore of silver called as silver glance. You add NaCN, water, you bubble air also, oxygen of air. Then you get a soluble complex NaAgCN taken twice. This is actually supposed to become Na2S, but because we are bubbling air, the oxygen of air will oxidize it to Na2SO4. On cooling, this will form crystals which are removed by filtration. Now you are left out with the soluble complex of silver. From this, silver can be obtained by metal displacement reaction. Only this part, this is filtered out. Only this part, remember, only this part is the leaching process. After this, what we do is NaAgCN taken twice is then made to react with zinc. This will bring about a metal displacement reaction. Zinc goes in and silver comes out. You get Ag plus Na2ZnCN taken 4 times. This is a soluble complex, so this can be removed by filtration. So this is another application of leaching process where ore is concentrated. See, when you dissolve Ag2S in NaCN solution and bubble oxygen, silver gets dissolved, but other insoluble substances can be removed by filtration. Even this can be removed by filtration. I have one more example. Just go through this, then I'll give you one more example regarding leaching. Example 3 for leaching. This is involved in the extraction of gold. As I told you, gold is available in its native form, but there are some impurities associated with it. So let us see how it is extracted from its natural form. Au, we use the same substance, sodium cyanide, in aqueous solution. This is called as hydrometallurgy. When you extract a metal from its aqueous solution, then you call it as hydrometallurgy. Then under these conditions, you get a soluble complex of gold, NaAuCN taken twice. Right. Now, during this process, we get all the gold dissolved as a soluble complex, sodium dicyanoaurate 1, and those substances which are insoluble are removed by filtration. Then obviously you do what is called as metal displacement reaction. You need to react this substance with a more active metal, then that more active metal goes in and the less active gold comes out. Look at this step. NaAuCN taken twice plus zinc and get Na2ZnCN taken 4 times plus Au. This is how we extract. The difference between these two is this is impure and this is pure to a large extent. We are discussing important stages involved in the metallurgy, in the extraction of metal. We have just now seen the first stage, that is concentration of ore. Concentration of ore is also called as benefaction, also called as ore dressing. The second stage is now conversion of the metallic compound in the ore into metal oxide. Conversion of ore into metal oxide. I told you previously, I would like to tell you once again that this particular step is involved in the conventional metallurgical operations, not involved in all metallurgical operations. This step is generally not involved in electrometallurgy. This step is not involved in hydrometallurgy too. But for most of the metals in the conventional metallurgy, this step is involved. We prefer transforming the metallic compound. Imagine if it is a sulfide, we prefer transforming it into metal oxide because reduction of metal oxide is easier when compared to reduction of metal sulfide. Why it is so, we'll be learning in the coming sections. Here, there are two ways of achieving this. This can be achieved by either calcination or by roasting. It is possible to transform metallic compound into a metallic oxide by either calcination or roasting. Let's first talk about calcination. In the calcination, ore is heated in a limited supply of air. Ore is heated either in the absence of air or limited supply of air. You get metal oxide as the. Now, during this heating, you lose all the volatile substances, volatile impurities from the ore. You lose sulfur, you lose phosphorus, you lose arsenic, you lose moisture. Moisture content of ore will come down and ore will get transformed into its oxide. Examples: calamine is transformed into zinc oxide and carbon dioxide. Fe2O3.XH2O is transformed into Fe2O3. I told you moisture content is removed. And then CaCO3 is transformed into CaO and CO2. So in this way, it is possible to transform the metallic compound present in the ore into metal oxide, and then reduction can be carried out. So these are some examples of calcination. Calcination is heating ore in a limited supply of air or absence of air. During calcination, moisture is lost, volatile impurities are removed, and the ore, the compound present in the ore, decomposes to get transformed into metal oxide. Now let's see what is roasting, and we'll see some examples of roasting also. ore is heated, here ore is heated in excess of air, excess supply of air, you get metal oxide. It is compulsory that sulfide ores should be roasted. Sulfide ores are roasted because the sulfur gets replaced by oxygen. Look at the examples. ZnS plus O2 gives ZnO plus SO2. The next example, PbS plus O2 gives PbO plus SO2. But here one precaution is to be taken, that this contains SiO2 as an impurity. Galena consists of SiO2 as an impurity. So if you roast galena, then PbO, which is formed being a basic oxide, will react with SiO2. This is something which is possible. PbO next moment will combine with SiO2 and will become PbSiO3. So it becomes important to prevent this reaction. To prevent this reaction, we need to add CaCO3. Then what happens, CaCO3, the limestone will decompose to give calcium oxide and carbon dioxide. Calcium oxide then reacts with SiO2 to give CaSiO3. So if this is present, calcium carbonate is present, then calcium oxide will be formed. It will prefer reacting with SiO2 to give CaSiO3. So there becomes a competition between these two to take place. Then calcium oxide is more basic. It is more basic in nature than PbO. So this reaction takes place in preference to this reaction. So in this way, it is possible to avoid wastage of PbO. So during roasting of galena, limestone is added. This limestone will decompose to give calcium oxide, which will react with SiO2, the gangue material SiO2, to transform into calcium silicate. In the absence of limestone, the PbO, which is formed during roasting, is likely to react with SiO2 to give PbSiO3, which would cause wastage of PbO. So the role of limestone is clear now. It is added to generate calcium oxide, which will take care of SiO2. Otherwise, SiO2 will cause wastage of PbO. I would like to add one more thing regarding roasting, one more example. If you have Cu2S along with FeS, then during roasting, you need to add SiO2. Then what happens? This FeS, this is the impurity present. It is the impurity. You have this mixture in chalcopyrites or copper pyrites. So during roasting, add SiO2. Intentionally SiO2 is added. Then what happens, Fe being more active than copper, it will transform, FeS will transform into FeO. Next moment, FeO will react with SiO2 and will be removed as FeSiO3 slag. So during roasting of copper pyrites, SiO2 is introduced. This will remove FeO as FeSiO3 slag. As long as FeS is present, Cu2S will not get oxidized because Fe is present above copper in the activity series. So it is more reactive, it is more prone to get oxidized. So this will become FeO. The moment it becomes FeO, it will react with SiO2 to become FeSiO3 and therefore can be removed from the ore. That's an advantage. We are discussing about the important stages involved in the extraction of metal. The third stage is reduction. As I told you, metals enter into chemical reaction by losing electrons. So to transform a metallic compound into metal, it is important that the substance should be reduced. So reduction is the important step involved in the metallurgical operation. Metallic compound is transformed into metal in this process. The various methods are: A, carbon reduction. Here we use either coke or carbon monoxide as reducing agent. Metal oxide plus coke gives metal plus carbon monoxide. There is also a possibility of this type of reaction. Metal oxide plus carbon monoxide gives metal plus carbon dioxide. So whether you use carbon or carbon monoxide, metal oxide will be reduced to metal, and the process is called as carbon reduction. Another way you can bring about this is metal displacement. This is done in hydrometallurgy. In hydrometallurgy, metal is extracted. In hydrometallurgy, metal is extracted from aqueous solution of its compound. So we have seen that NAAgCN taken twice when it is treated with zinc. Here zinc acts as a reducing agent. You get Na2, you get a zinc complex plus Ag. So this comes under metal displacement. You can also bring about auto reduction. Auto reduction. In auto reduction, a metal sulfide will cause reduction of its own oxide. Metal sulfide will cause reduction of its own oxide. Look, copper sulfide plus copper oxide. If you mix these two substances, then you get copper plus SO2. It's a case of auto reduction. A metal oxide is reduced by its own sulfide. Another example is this: PbS plus PbO will give Pb plus SO2. Remember, auto reduction is possible for mercury also. Auto reduction is possible for lead, sulfide, galena, even Cu2S, copper pyrites. Another way you can bring about reduction is electrolytic reduction. Electrolytic reduction, this technique is applicable for those metals which are themselves powerful reducing agents. This technique is applicable for extraction of active metals. For instance, Al2O3 is reduced to aluminium. This transformation is achieved by using electric current. But the problem is Al2O3 is a bad conductor. To overcome this, we add Na3AlF6. This is called cryolite. Cryolite solves two problems. It will decrease the melting temperature of Al2O3, fusion temperature of Al2O3. It will also increase the conduction. We use carbon rods, carbon electrodes. So here aluminium is reduced, Al is reduced from +3 state to 0, oxygen gets oxidized, later it will get transformed into carbon monoxide and carbon dioxide. The oxygen which is formed at anode will burn the carbon rods and transform into a mixture of carbon monoxide and carbon dioxide. We will be discussing extraction of aluminium in little detail later. So just remember that this comes under electrometallurgy, this comes under hydrometallurgy. These two, A and C, they belong to another type of metallurgy called as pyrometallurgy. So based on the way you do reduction, you have three important types of metallurgy: pyrometallurgy, hydrometallurgy and electrometallurgy. If you reduce by passing electric current in the molten electrolyte, then you call it a case of electrometallurgy. This is applicable for active metals. If you extract a metal from its aqueous solution of its compound, then you call it as hydrometallurgy. Here we introduce a more active metal and will be able to get less active metal. This is generally applicable for metals which are below hydrogen in the activity series, and you apply it for silver and gold. And then you have pyrometallurgy. Here metallic compound, especially its oxide, is heated with some reducing agent. Coke or carbon is generally used as a reducing agent. There are other reducing agents also. Then metallic oxide will get reduced to metal. So these are the three important stages. Another stage is refining of metal. We'll be continuing with refining of metals.